right. So the state of matter that we're going to discuss today, it's solid, and it's the one that we can think of as exact opposite of what gases do. So gases have negligible forces of attraction. Solids have really strong forces of attraction. Gas particles are far apart. Solid particles are really close. Gas particles, uh, they don't have much. They have a lot of kinetic energy. Solid particles have almost no or very little kinetic energy. So they're exact opposites of what gases do, and liquids are just in the middle somewhere. Now, based on what kind of substance you're talking about and what kind of bonding it has, solids will form different lattices. Now, of course, in all of them, there are a few themes that you will see. For example, in all of them, there is a regular pattern. In all of them, there is strong force of attraction. In all of them, there is rigidity that is there. But these solids, depending on what kind of forces they have, what kind of particles they have, the lattices can be slightly different. So I'll start with the one that you already know, the ionic lattice. And ionic lattice is the one in which you have positive ions, negative ions, both of them joined to each other. Usually we think of it as a lattice that is like this. So this is one way of representing it. So what's happening here is that you have sodium ions, chloride ions, all surrounded by each other. So you will see that there's a regular pattern. So these are all in a row and these are all in a row. And what's happening is that every chloride ion is joined or surrounded by every sodium ion, and every sodium ion is surrounded by chloride ion. Similarly, do you see the difference in sizes? Also, that the negative ions are not touching negative ions, they are exact kind of away from it. Now, if I want to look at the forces that they have in there, we can use this ball and stick model. And this model shows how the forces are in there, that basically you have these solid particles which have strong electrostatic forces. So these are electrostatic forces. And the forces are there because there's a negative charge on every anion and positive charge on every cation. And they have strong force of attraction between them. So what this means is that there is a continuous structure like this. And this structure is pretty solid. Basically, the forces are really strong and it's very hard to actually break it up. And if you try to do that, you have to supply a large amount of energy. So for example, if I were to show how this thing appears, it would be something like, let me share this. Yep. So this is a very simple sodium chloride salt model that you have. So you have these salt grains. Now I need you to make note of a few properties that this thing has. You can see that there is a rigid structure, all of them. You can see these edges over there. If you notice these edges, there are sharp edges there. No smooth edges there. जहाँ जहाँ से वो टूटा हुआ है, जहाँ जहाँ से वो particle है, sharp edges हैं. Do you notice that? And this is what salt particles might look like. Now, if I zoom in, this is a crystal. And this crystal, you can see that there's very rigid or sharp outlines. And there's a reason why that is the case, that all of them have a sharp outside border, or if you were to call it any such thing. Now, here's what it looks in the middle. So there is sodium ions surrounded by chloride ions. So you can notice that there's no physical connection in there. There's no hard line joining them. Koi black ya red line nahi hai. It's just that they're suspended in vacuum. And there is some distance between them. The sodium ions, they're all attracted to all the chlorides around them. So if you notice, one sodium ion is surrounded by 6 chloride ions. And similarly, one chloride ion is surrounded by 6. Ye piche bhi hai, aage piche har taraf ko hai. And you notice that they are kind of suspended. They're not really touching each other because this chloride is being attracted by sodium from all sides. So wo ek ki taraf zyada nahi hota. It's surrounded by all of them. So the forces kind of like give it a balance. Now here's the thing. This is the chloride ion formed by chlorine gaining an electron, and this is the electrostatic forces of attraction between cations and anions. You see, there is no force of attraction between chlorides that is being shown. And that's not because the force doesn't exist. The force does exist. It's repulsive. So these are attractive forces. तो आप देख रहे हो कि उनके एरोज बता रहे हैं that chloride is attracted to sodium and sodium is attracted to chloride. So that's how the forces are. And this is the lattice, and this is called one way of looking at it. This is the fill-in space model, and this one is a ball and stick method. And what's shown here is slightly different. Now we are not showing those arrows, but this is supposed to show a regular pattern first of all, like a mesh, and secondly, it's showing that there is force of attraction between oppositely charged ions. If you notice, so there's no force of attraction between between similarly charged ions. Force of repulsion है वो यहाँ पे shown नहीं हुई. So that is how salt crystal is the way it is. But we want to know two things. Number one, what effect do these strong forces of attraction have on the properties of the thing? And secondly, why are there these rigid, sharp outlines? So the idea is really simple. Because these are strong forces, they are going to make the compound pretty rigid, which means these ions are not able to move around. So that means no conduction. So they're bad conductors. And this is again something you know from O levels. They're bad conductors. They are excellent or good electrolytes. Electrolyte is something that conducts electricity in a liquid or molten state, liquid or solution. And they do because they do that. Similarly, solubility, they are usually not that soluble, usually insoluble, but in some polar solvents, they do dissolve. So except for some polar solvent. So water is a polar solvent. So there are some of them that are soluble in water. And you will study in A2 that why do some of them dissolve and why do most of them don't. But that's the general idea of how they're. So there's an infinite assembly of these ions and there's a regular pattern and the forces binding them are really strong. Those are the three characteristics that we have. So naturally the volatility is low. They are not that volatile because it is low, and that is because forces don't let them escape as much. And secondly, they have high melting and boiling point. Again, for the same reason, forces keep the ions close together. So it's really it demands a lot of energy to break the forces and melt the substance. So that's how these are. And about the sharp edges, why that is. So we know all of this from O levels. We know they have high melting point, volatility is low, bad conductors, good electrolytes. Usually insoluble. All of that is from O levels. That force of attraction is strong, so you need high energy to do any of these. But they're also hard. And why is it that they break so easily if they're that hard? So the idea is really simple. Basically, you have cations and anions in layers around each other, right? So that's how it may seem. This is how it may seem like. So you have cations surrounded by anions and all that. Now imagine if I were to apply some force on it. Let's say I push this one towards the left. The lower layer, I push it to the left. So what will happen? If I succeed in pushing it, then what happens is that I make something like this. This red one comes right below the red one at top, and blue one comes right below the blue at top. And what happens? A very strong force of repulsion applies. They repel each other because they're the same charge. And the force is so strong that they're going to give it a sharp cleavage right here. The crystal breaks up. And that is why they have these sharp edges. Because वो जहाँ पे किसी और को हल्की सी force लगी, the oppositely charged ions were attracting, but like charges repel with a force that is more than 18,000 times stronger than the force of gravity. And that is why they repel and they just separate right away. The crystal breaks up. And that's what happens in these. Okay? Okay, so here's a question. We use magnesium oxide in these electric furnaces. A furnace ke andar, we are obviously baking something, we are heating something, but magnesium oxide se furnace ki inner lining bana dete hain. Why are we doing it? Why is magnesium oxide a good choice for that? Again, it is a good choice because Uh, this doesn't conduct electricity, so there's very little leakage of current, and the forces are strong, so it withstands this high heat energy that is being applied in there. Okay, so yeah, that's why we use it. Now, the second lattice that I want to talk about is again something that you've studied in O levels. This is metallic lattice. So this is the second lattice that we have here. Now, this is different from the first lattice because the first lattice was oppositely charged ions, but this one is just similarly charged ions. And there is a cloud of electrons. So this gray thing is supposed to be a cloud of electrons, free electrons, in fact, or mobile electrons. And they're able to move around. And there's so many of them, we call them sea of electrons. So they're like offloading these valence electrons that they have. They're just throwing them out. And that is how they get noble gas structure. So there are layers, but notice that no cation is touching the other cation. Of course they can't. They're going to repel each other if they ever do that. And that is exactly what happens if you try to push them. If you try to push one, you press on them, the cloud keeps them close to each other and all that. Now, let me compare sodium with magnesium. So sodium and magnesium, I have their lattices. So if I were to compare them, this is how the lattice might look like. In sodium, you have randomly placed electrons. Notice that the electrons don't have a pattern, but cations do. And similarly, in magnesium, electrons don't have a pattern, but the cations do. But notice that in sodium, there's smaller charge. And that is why they are also further away from each other. Do you notice that? The particles are actually further away compared to the ones in magnesium. And that is because in magnesium, the charges are stronger, so they're closer together. So metallic bonding in magnesium is stronger. We would expect magnesium to have higher number of electrons in the cloud. So every magnesium atom is donating 2 electrons and every sodium atom is donating 1 electron. By the way, in A levels, we don't use the word losing electrons. We prefer saying donating electrons, although preferred nahi padta. So this is how the lattice is, and magnesium will have higher melting point. It will have higher boiling point, all of that. And that is because the lattice is stronger. Okay. So that's how they are. Now, again, if I apply force on one of these lattices, so let's say I have a lattice and apply a force on it, what will happen? Exactly what happens in the other lattice that I saw. Because right now they're randomly arranged, but if I were to push them, one cation is going to come exactly opposite to the other cation. And that is not good because then they repel each other. And that red line is supposed to show strong area of repulsion. And that is why they make very clean, straight edge when they break. So you will see that the edges of metallic things are sharp and they form these straight patterns. You can make a really clean slate over there. You can have a very sharp surface over there. And that is because they have these, whenever they break them, they break across the whole lattice because every cation is in sync with the other oppositely placed cations. The charges are the same, so they repel each other. So this makes them malleable, this makes them ductile, this makes them sharp. We use them to make knives. Why? Because we can make very thin, sharp edges because of these things. So that is metals. And you know this, you have seen this in O levels. And I don't think there's anything new here. So that's what happens. But you can change this a little bit. You can do it because if you have an alloy, that alloy will override this property of metals because in alloys, so this is supposed to be an alloy. And let me compare it with the pure metal. So this is a pure metal. So if you take this one, the pure metal, and you take that alloy, you will notice that alloys have differently sized particles in there, which means that now the layers don't slide that easily. You apply a force and it wouldn't slide that easily. And that is why alloys are rigid, more rigid than pure metal. They are not that soft. And so that does offer an advantage because they're soft structure. We can't really use pure metals. They're so soft, so ductile, very highly conducting of both heat and electricity, but they're not that strong. So we can't really use them to make different things. I don't want to make a bridge that is soft, and I don't want to have a gate that is soft. But you add things in there like carbon or even other metals, magnesium, silicon, manganese, copper. You add those things, and these alloys, they get best of the both substances in there. So iron rusts, but carbon doesn't. So you add carbon to iron and chromium, add that, and you have stainless steel. You want something that is light but still strong. Take aluminium, add other things in there, and you have very lightweight but very strong and uh, resistant to corrosion thing, because aluminium doesn't rust. Aluminium is low density, relatively low density, but the alloy is much stronger. So you can make aircrafts from there, or cylinders of these uh, car engines, because the shaft has to move on and all that. And even bicycle frames, because bicycle frames are supposed to be light. The really light bicycle frames go for hundreds of thousands of rupees, because the bicycles become very expensive because a better alloy is being used, which is strong but also very light. So you are combining best of the both of these. So these are what alloys do. So for example, uh, you might know about bronze or uh, brass, which is used to make statues or furniture and all of that, and it has a very good shiny luster because it's made from metal, but it's also very hard because it's an alloy. So alloys offer an advantage that pure metal might not. Now now the third kind of lattice, and this might be new to you, is we never really talk about what happens when you solidify molecules. Like we do talk about ice, that ice forms a lattice, and that is a crystal lattice, and all the properties of water and ice having these peculiar properties. Like ice is less dense than water, and ice floats because of that. All of that comes from these lattice that molecules have in ice. But what about if I were to like solidify something like chlorine, or just a simple thing like a simple molecule? I just solidify it. Now it doesn't have any charges in there, so molecules are just going to come close together. They are really close together, but there are also weak van der Waals forces because of dipoles that are created on them when they come close to each other. And those dipoles are there, right? So for example, if I were to solidify, your book talks about iodine. So let's say I have this solid iodine. This is how it might appear. So this is molecular lattice. Okay, simple molecular lattice. So what's happening here is that everywhere they're close to each other, there are dipoles forming. The dipoles are because the electron cloud is repelling the other electron cloud, and there's a redistribution of these electrons. Okay. All right. So simple molecular lattice is like iodine molecules or anything that has instantaneous dipole. When they come together, there's not a regular pattern, and when you give them even small amount of energy, these molecules will like vibrate, and they will just go their separate ways. That's what happens there. All right. And now we have to talk about two other kinds of lattices that you are already familiar with. One is this picture might be familiar. So, for example, this one. Any idea what this is? Do you remember? Or if not that, then this will definitely be very familiar. These are diamond and graphite. They're two different lattices that we have. And they're not just diamond and graphite. There's also silicon dioxide that shows this. Let me show you the structure of silicon dioxide. So this is the structure of silicon dioxide. So the red ones are supposed to be oxygen, and the yellow ones are supposed to be silicon. Okay, and you can see that there is 4 oxygen joined to every silicon, but every silicon is joined to 2 oxygen. Sorry, every Yeah, one oxygen is joined to 2 silicon, and one silicon is joined to 4 oxygen. So the ratio is 2 to 4, which is why the formula is SiO2. Even though you have so many of these oxygen and silicon atoms, it's not like usme SiO2 का कोई molecule है. It's simply that the ratio is 1 and 2. And you will see that there is a regular pattern here. In all of these lattices, the formula comes from the ratio of particles, not from the number of particles. It's only in molecules that we get actual number of atoms in the formula. So this is graphite, this is diamond, and we remember three main properties. The melting point is really high in both of them because the forces of attraction, the covalent bond that you must break before you separate every atom, they are really strong. So that's one. Secondly, all of them will not conduct electricity because there's no free electrons. And then they are very strong, they're very rigid. Okay. And again, because every atom in there, whether it's carbon in graphite, in diamond, and whether it's silicon or oxygen in silicon dioxide, they're very rigidly bonded to each other. So they make this tetrahedral structure. And whenever you melt it, you have to actually break all the covalent bonds. I remember that in O levels, we usually tell students not to mention the word bond, but in A levels, there's no such restriction. You can say that the bond must be broken, which is in fact true. You do have to break the forces and the bonds that are in there, the covalent bonds. Now, graphite is slightly different because in fact, it's exactly opposite because graphite has high melting point, sure, but then it's a good conductor because every carbon atom has 3 electrons in there that are bonded and 1 electron that's free. And then they are soft because these layers, they can slide over each other, as we know, because there's weak van der Waals forces. As you can see in the dots, they're weak van der Waals forces, so they can slide over each other. So that's how they are. And we have seen this earlier on as well, that how graphite works when we were talking about covalent bonds. Yep.
The weak van der Waals forces are between the layers.
Yep. Now there is an idea of allotropes that we must know. Carbon and graphite are both allotropes of carbon. Diamond and graphite, they're both allotropes. Allotrope is, there's 3 things that it must have. So an allotrope is a different structure of same element in same state. Okay. So it's the different structure of same element in same state. So it's important that if you're talking about allotropes of, let's say, oxygen, both of them should be gases like ozone and oxygen gas. But carbon, you have diamond, graphite, you've seen them. But there's a third family, which we call fullerenes. And fullerenes, one of them is this one, Buckminster fullerene. These are molecules of carbon, individual molecules that form these football-like structures. And they have low sublimation points. They don't really melt. They are sublime in room temperature. And they have room pressure, So they have low sublimation points. Why? Because these molecules have weak van der Waals forces between them. And they're bad conductors. Why? Because there is very little delocalization of electrons in there. The electrons are not free. And because it's molecular, they are more reactive than graphite. So this carbon, Buckminster fullerene, or even any other fullerene, will be very reactive to hydrogen, fluorine, oxygen, chlorine, bromine, all of them compared to graphite. And diamond is very, very less reactive.
Why is more reactive? Graphite?
Why is it more reactive? Number one, the surface area. It is more exposed. Number two, there's less number of forces, less strength of forces that must be broken for this to react. Graphite means the whole lattice has to break now. But in here, you can just work with one individual molecule and it will react. Now, if you had this same fullerene, but you joined them in long arrays, long tubes, if you had that, this thing is called a nanotube, CNT, carbon nanotube. So what I've done is I've taken graphite and I've folded it on itself. Or we can say that this is fullerene joined together in this layer, and this layer is made into a cylinder. This thing is very good conductor. Why? Because just like graphite, it has free electron. This one also has free electron. Because if you notice, every carbon atom in there is joined to 3 others. So the fourth electron, it's free. And now it can move inside the cylinder as well. So it has a very high electrical conductivity. This is also very strong because this is kind of a lattice. So it's hard to break this. And you can actually use them to make wires, to make electrodes, make clothes, make, I don't know, different structures from these. This thing is so strong because there is a lattice, this is rigid, high melting point, high strength, high electrical conductivity. This is actually stronger than a bulletproof steel. And the problem is that it's kind of hard to make this thing, which is why we don't make our cars with this. Otherwise, we do use it to make many, many different things, especially in high budget industry. Like अगर आपने स्पेस शटल वगैरह के लिए काम करना है तो उसमें इसका बहुत ज़्यादा यूज होगा, स्पेस सूट्स वगैरह में. Now, if I took just one layer of graphite, just one layer, that will be something like this, right? And this thing, so this was CNT, this is fullerene, and this one is called graphene. It is one layer of graphite. So this has very little force of attraction compared to graphite. So this is very reactive. And it has low melting point because of the same thing. And it's not entirely rigid, so you can shape it in a way that you want. But yet, it is strong. And again, every carbon atom is joined to 3 others. So this is good conductor. So carbon, पहले तो हमें पता है कि carbon plays a very important role in life, but even in industry, you can see carbon कितना versatile है. And you can use, there's a whole lab in LUMS that is just working on graphene. So that's how versatile carbon is. और बात आ जाके वही रहती है, 4 bonds हैं तो बिजली कंडक्ट नहीं करेगा, 3 bonds हैं तो करेगा. Or depending on the how big the lattice is, it will be rigid. So in diamond, the lattice is really big, so the whole thing is like connected like that. So it is very rigid. But in graphene or graphite, वो lattice उस तरह से नहीं है. It's not, it's going across like X and Y axis, but not Z axis. So that is why it is soft. That is why it conducts like that. And it does conduct electricity because every atom is joined to 3 others. So you can see that fullerene can conduct electricity, but because it's molecular, move करता है बहुत ज़्यादा and all that, sublime करता है, तो वो उतना अच्छा conductor नहीं है. But CNTs, graphene, graphite, all of them, they are excellent conductors. And these are all different allotropes of carbon. And by the way, you can use it to make other structures. सिर्फ pure carbon use करना ज़रूरी नहीं है. And no wonder we use it all the time. We make different plastics from carbon compounds. And this thing is so useful. मतलब एक example देते हैं, हमारी जो गाड़ियाँ हैं, for more than 40% of our cars are now organic. They're made from these carbon के material. और मतलब सीधी सी बात है, आयरन को आग लगती है, गाड़ियों को तो लगती है आग. तो अगर उसमें सिर्फ आयरन होता, सिर्फ मेटल होता, तो उस तरह से तो ना आता. तो आधा हॉलीवुड का बिजनेस खराब हो जाता अगर कार्बन की ये प्रॉपर्टीज ना होती. But that's on a lighter note. Otherwise, we do know carbon is being used. All these allotropes, they have their own advantages. Fullerenes are recently discovered. CNTs, graphene, even recent. Malab graphene hasn't been known for like, I think less than 20 years. Graphene जो इस पे काम होना शुरू हुआ, and they have tremendous industrial potential. लेकिन obviously वो हमें real effects उसके थोड़े से बाद नजर आएंगे. Maybe 10 years from now, or maybe one of you might be working on one of these labs. Anyways, so yeah, that is what solids are. And the 5 different kinds of lattices we have seen. We have seen ionic lattice, simple covalent lattice, macromolecules. We have seen different allotropes within macromolecules, and we have seen metallic lattice. Okay.